Okay, practice problem 2. We're back to acetic acid. I sort of erased around the top of my board because it's still acetic acid. So it's still Ka, pKa, Kb, all the same, and we're good. So I also added my moles of HC2H3O2, my moles of acetic acid, so I can easily tell if I'm at the equivalence point or not. So beginning one, 0.0 milliliters added. I'm just calculating the pH before addition. I bet it's the same as last time I did this for acetic acid, but if you remember, before the addition, it's a pretty easy setup. I'm not even going to show my ice chart anymore because we are so set on ignoring x. Ka is going to be x squared over my concentration, which I believe here I was looking at 0.100 molar. My equation I got this from, just so you know, HC2H3O2 is going to break down into H plus, and I'm probably going to run out of room, C2H3O2 minus K. I'm using that to get to this. That's X, X, and I ignored that. I pretended that never happened. When I did this, I got that X equaled, and you guys can solve for this yourselves, especially if you're trying to work through the problem on your own. This one was easy. All I'm getting to solve this, I get the same as every time. I got 0.00134. That's my concentration of H. Negative log of that gave me a pH of 2.87. I think it did last time I did this too. Acetic acid, always, that seems to be what happens. This is before the addition of anything. You always do that. Dissociation of the acid, acid dissociation constant, solve for X, that's concentration of hydrogen. That one's easy. So the next thing I do, and we don't really need that, but I think the next couple I'll use the same equation. It looks like I was just told that I'm adding OH minus to this. So, okay, what am I doing? I'm taking an acid here, H3O2, and I'm adding a base. That's gonna mess things up. That's gonna give me C2H3O2 minus and water that nobody likes. No one cares. That's my base neutralization equation. So, before the equivalence point, I'm looking to use the Henderson-Hasselbalch equation since it's a buffer. Before equivalence point, buffer. Good Henderson-Hasselbalch. But what am I doing here? So I have, let's do moles. Let's look here and say if I have, first of all, and I'm going to put it down here so I can use up here, in 0.005 liters of this stuff, it was 0.200 moles per liter. So my number of moles I just added is going to be 0.001 moles, or probably 0010 significant digits-wise, of OH. I got that from 5 milliliters times my volume. Just keep your eye on that. I may not show the calculations for the molarities very often because I'm hoping you remember how to do those. So what did I start with? 0.00250 moles of acetic acid. I added 0.001 moles of OH. What this is going to do, that's going to go away. It's going to react. The OH is going to make 0.001 moles of sodium acetate, my base, and it's going to take away 0.001 moles of my acid to make that base. 0.0015 mole there. Cool. So what that gives me is pH is going to equal my pKa, 4.74, plus log of base over acid, and we said that's the acid with the hydrogen, so 0.001, and 0.0015. Let me make a note here. I didn't even bother converting to molarity, because if I did, I would divide the top by a volume, I'd divide the bottom by a volume, and they cancel out. Because you're doing the same thing to both parts of the fraction, so who cares? Like water. No one cares. No one likes water. So we're good. When I solve for this, easy calculation, I've tinkered around here. I'm not to the equivalence point yet. I bet I'm not to the half equivalence point yet, I don't even think. So I'm expecting not too much of a difference from my pKa, but I got 4.56. Is it up from where I started? Oh, yes. If I look at my 2.87 to start, I have come up. So if you look at the next part, the 10 mil, if there were 0.001 moles in 5 mils, I bet for part 2, and if you want to pause right now and calculate it, I bet that it's 0.002 moles. It works the same. I still haven't gotten to the equivalence point at 0.00250. So if you want to stop and try the same thing for the addition of 20, go for it. I'm going to keep going, and I'm going to be the lazy teacher and just make my little changes because of the wonders of dry erase. I just changed all my 1s to 2s and moved some extra stuff here. I am looking at a difference, though, in my ratio of base to acid, because this is now 0.02, and that's real low. That's mostly used up. I'm almost to my equivalence point. But I'm still using the Henderson-Hasselbalch because I'm still below the equivalence point, moles of acid, moles of base. Henderson-Hasselbalch's your best friend. When I did this, though, you're starting to see more of a reaction, more of a change. My pH for this new value is even more, it's creeping up to more basic. I got 5.34 here. I haven't quite gone up over yet, but I'm getting there. I'm getting there with equal moles of base and then past. So that's still before my equivalence point. Flipping page, I've got more. Oh boy, this is the excitement. We're at the equivalence point. Remember, at the equivalence point, we flip over to a base equation because all of the acid has been used up. So the equivalence point is a big deal. I'm not even going to set it up because I know what happens. I know at the equivalence point, the acid is all gone. All gone. It reacted with the same amount of OH minus, and what it's made, right now, I know that at the equivalence point, I now have 0.00250 moles of the conjugate base. Because all of the acid is reacted out and has all been converted to its base by OH. OH stole its protons. So, I will need in this case my total volume. This is different because we're back to molarity and using concentration of OH. So my total volume here is going to be, it's going to be 12.5 from here. I hate milliliters. 0.0125 liters plus, I think it was 0.0250 liters up there. That's just gross. I guess liters goes outside parentheses. That's gross. That's unnecessary. I hate milliliters. Millimolar time. So what I ended up here with my molarity was 0.0667 moles. You'll also notice these concentrations are really small, and it's a real pain in the butt to remember how many zeros you have. I can't count how many times I've been like, that's 1 0. That one looks like 3. Is that a 0? Be very careful with decimals and zeros and exponents here because these values are very small. What I do once I get to the equivalence point, I need a KB equation. I need a KB value. So what I'm looking at is this base. What's it going to do? It's going to make C2H3O2 minus. It's going to mess around with the water no one cares about. And what's it going to make? Well, it's going to snap up some of their protons, C2H3O2, and leave me OH. Leave me this pH determiner OH minus. So, I'm good. I've got KB. I've got molarity. No one cares about water. And this is where I just put in that equation with the x's that, and we know we're going to ignore x on this side. So 0.667 molar. It would have had minus x. We're not even going to bother with that. My values on the other side, and again, this is just a condensed version of the ice chart where you would have 0 and 0, minus x plus x plus x. So we now have x and x, where KB equals x squared over 0.0667. That's molarity, but okay, no one cares. No one cares about molarity either, just like water. KB, 5.6 times 10 to the negative 10th. Because I memorized that, I'm not even kidding. When I solve this out, my X is going to equal my concentration of OH, which will determine my pH, and that's going to be 6.11 times 10 to the negative 6th. To get my pH is going to be 14 minus the negative log of that. I expect a basic pH, the equivalent point, weak acid, strong base, and I get what I expect, 8.79 for my pH. If you guys are coming up a unit or a tenth, a hundredth off on these, it's rounding. I'm not concerned if you're close. Last but not least, I believe I called this a blown buffer yesterday. We are past the equivalence point and we still dump in base. This is the pink that just keeps pinking. Notice I got as close as I could to a phenolphthalein color for you guys today. I'm teaching in phenolphthalein to honor titrations. So, here we go. 15 milliliters, 0.0150 liters times my concentration, 0.200 moles per liter, gave me a whole pile of moles. 0.0030 moles there. This is past the amount of H2C blah blah. Yes. 0.0030 moles of OH minus my 0.00250 moles of acetic acid, HC2H3O2. What does this leave me? This leaves me 0.0005 moles, there's more zeros after that for my significant digits, but we're good, of OH minus. What's my total volume? I started off with 0.0250 liters. This is 0.0150, so I'm going to have 0.040 liters here for a concentration, 0.0125 molar OH. After the equivalence point, all that's going to determine my pH is that OH. So now, pH is going to be 14 minus negative log of my concentration of OH. Solve, solve, solve. I get a pH of 12.10. Very high pH, very basic pH, what you'd expect from blowing out the buffer. Too much base, the super pink titration for our strong acid, strong base, yeah. Past the equivalence point, concentration of OH goes to pH. So the takeaway message, before the equivalence point is your Ka expression. That's what, sorry, even before that. Before addition of anything is your Ka expression. Before the equivalence point, Henderson-Hasselbalch. The equivalence point shifts you over to your Kb with your x squared and your ignore x. And for your past equivalence point calculations, go with your excess OH minus and calculating pH from that. This will work. So hopefully this gives you an idea of how to on these. One more video in the series coming up of a weak base, strong acid.